Hello and welcome to Lecture 1 from AP Physics 1. We're going to talk about Chapter 1. Now, lots of these things you've already discussed and already thought about when you did your summer assignment, and you read the first chapter of the OpenStax College Physics textbook. These notes are going to come out of the first chapter of the Cutnell and Johnson textbook, which is the blue one I gave you in class. So let's get started. Now, I know you studied a lot of science. You've studied biology, you've studied chemistry, and so you've talked a lot about what the goal is of science, and physics is no exception. Physics developed out of the efforts of men and women, lots of things to say here, to explain our physical environment. And what does that mean? Well, science is actually sorted into two main categories. We consider them physical sciences, which are things like physics and chemistry. They describe parts of our world that are non-living. And the other is life science. And life science is things like biology and physiology. And they describe the complex systems that create living things. Physics describes all the building blocks that allows nature to build up those complex systems. And physics actually encompasses a huge variety of stuff. It's things like orbits and radio waves and magnetism and electricity and optics and lenses and motion and forces and acceleration. It's the reason that the planets turn the way they do, and it's the reason that atoms interact the way that they do. And we are constantly trying to find a way to describe our physical world, to predict what will happen next. But to do that, physics requires a great deal of experimentation. And physics experiments can cover a huge variety of things. So we need to have some way to measure that we can get data that's not only accurate, meaning correct, but also reproducible. We want results that not only I can get, but you can get, and a physics student halfway around the world could get. Because if I publish a finding, if I say, oh yes, I've proven that the sun revolves around the earth, but no one can predict or reproduce what I've done, it's not really a valid piece of science. So the first step to ensure the accuracy and the reproducibility is to agree we're all going to play by the same rules, and we call that set of rules units. Now here in the United States, we use an unusual set of units, but they aren't going to be the ones we use for physics. And the reason is, and I'm sure you've heard this before in chemistry, because science is an international adventure, and we all need to agree to measure things in the same way. So what we're going to use are what we call SI units. And SI stands for, let me write it down for you first. The problem is that it is French, and my French accent is terrible. So it's the Système International. And the reason that we use the French title for the International System of Units is because it was codified and based in Paris. And explicitly, we're going to use what we call the MKS system, the meter kilogram second. And these are our three most important, most common units. So, how do we know how long a meter is? Well, because we used to have one. This is an image of the original meter, created and stored in France. It's in a vault outside of Paris. It's made of platinum, and it is the meter against which all other meters were measured. But here's the problem. Every time Fisher Scientific wants to make a meter stick, they can't go to France and hold up their meter stick in the vault next to the meter and make sure it's the same length. So the way they dealt with that was to create a set of copies. I believe there were 8 of them, but you don't quote me on that. I'd have to look it up. And one of them is stored here in the United States, and it's stored at a place called, whoops, I'm hitting a button with my finger. Excuse me, let me get my pen back. And it's stored at a place, boy, that's not green at all, is it? Called NIST. And NIST stands for the National Institute of Standards and Technology. There's a Y on that. And NIST is located in Gaithersburg, Maryland, and it is the governing body responsible for maintaining the standard use of measures in the United States. For example, when you buy gas and you pay $2.90 a gallon, how can you be guaranteed that you are getting a gallon? Well, NIST is ultimately the agency that guarantees that what we say a measurement is actually what a measurement is. And in the United States, NIST was responsible for maintaining the meter. But it's very difficult for Fisher Scientific to go to Gaithersburg and compare against the meter. So they made another copy, and another copy, and as you might expect, a copy of a copy of a copy of a copy eventually starts to get some error. And so now, a meter is described as how far light travels in 1/300 millionth, give or take, of a second. That is the new standard of the meter. The kilogram, however, is still measured against this thing. And this is a platinum kilogram that is stored in the catacombs in Paris, and it is in, those are vacuum jars to keep the air from eroding any of the surface and changing its mass. So, back to our units of measure. We already talked about the SI system, the meter, kilogram, second, MKS SI system. You've actually used the metric system, imagine the air quotes there, the metric system before. In chemistry, however, they use the CGS system, the centimeter, gram, second. And the reason is because generally in chemistry we are dealing with things that are very small, and we want to scale our system of units in such a way that we can deal with those tiny things more effectively. Now in the United States, we use the British imperial system, and it is the foot, which you are familiar with, the slug, which is a unit of mass, and again a second. But the British system is unwieldy, and it's counterintuitive. I mean, there's 12 inches in a foot, and there's 3 feet in a yard, and there's 5,280 feet in a mile. And it's hard to predict what the next size will be. So using the metric system is going to be a lot simpler in the long run. And part of the reason for that is because we can use those units, those MKS units, those base units, to build other units that we're going to need later. We can derive more complex units using our base units. There are, in fact, 7 base units, and we'll get to all of them later, but the most common are the meter, the kilogram, and the second. And we can combine them to measure things like force and energy and power. We can use them to measure torque. We can use them to measure velocities and accelerations. And we will continue to combine these units in new ways, but it's always going to come back to those 7 base units. So, in order to use units, we have to be able to convert between them in a reasonable way. And here are some common unit conversions. Now there's a list of these. I believe it's in the front cover of the blue textbook. If not, if you go on Google and type feet in a mile, it'll come up right on the main page. But for an example, 1 foot rounded to 4 decimal places is 0.3048 meters. So it's about 1/3 of a meter, which should make sense to you because we know a meter is slightly longer than a yard. A meter is just about 39 inches, give or take. 1 mile is 1.609 kilometers, or 1,609 meters. If you've ever run a 5K as a runner, you'll know that's just about 3.1 miles. A horsepower is a measure of power. And it comes out to be 746 watts. So just about 8 big light bulbs. And a liter is a measure of volume that converted poorly to my screen. So we generally write it like this, 10 to the negative third cubic meters. Okay, so that is the same as 0.001 meters cubed. Okay, so let's do an example. Let's consider the world's highest waterfall. So the highest waterfall in the world is Angel Falls in Venezuela with a total drop of 979 meters. Long way, huh? So since we have no sense of how long 979 meters is, being arrogant Americans that we are and unwilling to adopt the metric system, we're going to try to express this drop in feet. The first thing you need to know is right there in red. We know that there are 3.281 feet in 1 meter. So what does that mean? Imagine if we divide both sides by a meter. Then we'd get 3.281 feet divided by 1 meter. Since they are equivalent, that's the same as 1. And that is the secret of unit conversion. Because we know from math class when we're very young that any number multiplied by 1 is going to give us that same number back. And so we're going to try and take our quantity, 979 meters. So we're going to say that length is equal to 979.0 meters. And that 0.0 is important, and we'll talk about that later. And we're going to multiply it by a fraction that's equivalent to 1. But I want meters to go away and feet to remain. So if I have meters on the top of the fraction here, I'm going to want to put it on the bottom here. So 1 meter is equivalent to 3.281 feet. Now, because I have meters at the top and meters at the bottom, I can cancel them out and I'm left with feet. So if you were to plug that in your calculator, please don't feel like you have to do it by hand, but I already did it and it comes out to be just about 3,212 feet. That's more than half a mile. Crazy, huh? Okay, so the problem with this 10-base system is that it's not always reasonable to express everything with lots of zeros. So we don't want to write things like 0.000000001 meters because that's unwieldy and it's easy to forget a zero. So being the reasonable and utterly useful system that the metric system is, they have assigned a set of standard prefixes. And we use those prefixes to denote multiples of 10. And here's what they are. They go all the way from tera, capital T on our chart. They actually go further than this, but these are the only ones we're going to care about because we're never going to get outside of this. And you've actually probably seen the prefix tera. And the reason is because now computers actually have terabytes of storage to them, meaning that your brand new 1 terabyte laptop can hold 1 times 10 to the 12th. So a 1 with 12 zeros, bytes of data. That's unbelievable. Giga is billion. It's a capital G, 10 to the 9th power. It says at the bottom, there's a little note there you can't really say. It says pronounced giga. That being said, I've almost always pronounced it giga, and most everybody everywhere does. Mega, capital M, is a million. So a megameter is a million meters. A kilometer, a kilometer, is 1,000. Hecto is 100. Hectometer is 100. Deca, with a K, D-A-M, would be 10 meters. Decimeter, you've heard this before, decimal. Centimeter, you've heard of that. Millimeter. This funky letter here for micro, is actually a Greek letter. It's called mu, and it's just a U with a long tail at the beginning. And micro means 10 to the negative 6th. It's a millionth. Nano is a billionth. So when you hear about nanobots in sci-fi movies, it's actually a indication of size, believe it or not. Pico is 10 to the negative 12th. Femto is 10 to the negative 15th. Now, listen to me carefully. I expect you to know this. We'll talk about it tomorrow in class, but sometime soon, I am going to give you a blank table with simply the factors in it, just this column, and you will need to correctly list the prefix and the symbol. Spelling counts. This is a very easy set of points, but we are going to use these, and I expect you to know them. So please, take a note of this. You'll notice it's table 1.2. It is in your book in section 1.3. Look it up. So, let's get a strategy of how to convert between units. Okay? The first, and most importantly, in all calculations, write down the units explicitly. And I mean explicitly. I don't mean write units willy-nilly as they suit you. If you write the units in, you won't forget the units. In addition, on AP exams, units matter, and I expect you to use them appropriately. Because if I find out you didn't get points without units, man, I'm coming after you. So second, treat all the units as algebraic quantities. Blah, blah, blah. What that means is, if you have one at the top of a fraction and one at the bottom of a fraction, you can just cross them out. And finally, you need to use conversion factors. You're not allowed to just use any numbers you want. So use the conversion factors. We'll try to make a copy out of your textbook, but if you need them, they're on the page facing the front cover. So let's do an example, a slightly more complicated example. So we're going to express the speed limit of 65 miles an hour in terms of meters per second. So take a minute, and I want you to think whether or not you believe that the number of meters per second equivalent to 65 will be a number smaller than 65 or a number bigger than 65. Do you think it will be 20 meters per second, or do you think it'll be 100 meters per second? So think about that as we get started. All right, so let's talk about speed. Okay, the speed is equal to 65 miles, don't just use an M because that's meters, per hour. When we say per, we mean divided by. Okay, so let's think about what we're trying to get to. We are trying to get to meters and seconds. Now, there's no way for me to turn hours into meters or miles into seconds. So I need to do two things. I need to convert miles into meters, and I need to convert hours into seconds. So I'm actually going to do this in two pieces. Okay, I'm going to start with the top. I know that 1 mile, and I want to put it on the bottom because I'm trying to divide, is 5,280 feet. So now I can cross out miles. And I know from my conversions above that 3.281 feet is a meter. I can cross out feet. You'll notice I'm left now with meters, which is what I wanted. Now, notice the number doesn't always go on the top. Sometimes the number goes on the bottom. Be careful to always leave the number with the unit. Now that we've dealt with our distance, we can deal with time. Now, though, hour is on the bottom, so I want hour to be on the top. 1 hour is 60 minutes, and 1 minute is 60 seconds. So an hour is 3,600 seconds. Now I can cross out hour, and I'm left with meters over seconds. So now we multiply across the top, 65 times 5,280 divided by 3.281 times 3,600. And if you plug that all in your calculator correctly, you're going to get just about 29 meters per second. So, is that what you guessed? Did you guess that the meters per second value would be smaller? A meter per second is very quick. Please be aware of that when we're doing velocity calculations later. Okay, we're going to stop there in this lesson. If you have any questions, feel free to let me know. And we'll work on problems like this in class.